Hello again, and welcome back again to the series of videos, short videos on simple input output in C. We reviewed first fgetS, which is to read strings. We reviewed fscanf, which reads formatted data. We reviewed fread, which reads bytes. And we said, as we will in this video, let's apply fread and its companion fwrite to writing structs out to disk in binary format and reading them back in, because that's another good application of fread. Here's an example of fread, which we went through in the last one. Here's an example. Here's what we're going to do, at least in a code example in just a minute, with fwrite and fread. So we'll define a struct. In this case, I'm going to reuse the phone struct. It's already out there in Canvas, I think, in phones.h. It describes some of the attributes that you might capture to describe a particular instance of a cell phone. We'll put some data into it because it's an empty struct is pretty boring. We'll fwrite a couple of them out to a file. So we're basically persisting the data about the phones on disk. We'll take a little side trip and look at the raw file contents, because you need to see what actually got written out to understand what fread is doing. And sometimes folks are confused because they write the file out with fwrite, they open up with the text editor, and it looks really wrong or really weird. And it isn't. So I'll explain why that is. And then we'll read the file back into our struct using fread. So that's what we're going to do here. So let me get the code here, and we'll share that. Okay, this is the code for an example, a complete example, most of which is already out there in a version on Canvas of creating a phone struct, populating that phone struct with data, and then displaying that phone struct. What we're going to add is writing that phone struct out to disk with fwrite and reading it back in with fread. Just to refresh, here in phones.h, if I can find it here, phone.h is the actual struct we're going to be using. Notice it's got the guards to prevent multiple inclusion, and a phone, which is a struct we're defining with our type def, has a color, storage, a size, a model, a manufacturer, and a camera megapixels. So we're going to go and populate some or all of those, write it out to disk, read it back in again, and make sure it still looks right. The code to do that is in phonetest.c. So if we go to the top, we'll see this should be starting to look familiar, because all of these input-output programs that I'm demonstrating are very similar in principle, and they're very similar to programs you've already written in class. There's a hash include for standard.io.h. As I'm sure you know now, that's where the definitions for fwrite, fread, fscanf, fgetS live. That's where they come from. That's how the compiler knows what those functions look like, so it can go and include them into your executable file. There's also a hash include for string.h. We finally need it in this example. I have been just superstitiously including it before. It doesn't hurt to include extra header files. It doesn't do any good, but it has minimal impact on your code. This time we actually do need string.h, because we're going to need strcpy to put data into that struct, to populate some of the information like color and model and manufacturer in our struct. Here is phone.h. Now this is the one, these two files right here are of course part of the C standard library. This file is the header file that we created. So we're hash including phone.h, which means our program has access to that whole type def that defines what a phone looks like. So now we have a type called phone that we can use just as if it were a built-in type. I made a function print phone, which is just a convenience function. It's basically just one long printf. If it looks a little weird to you, it's just because I broke the printf on the multiple lines to make it a little easier to read, and so it wouldn't scroll off the screen. But it prints the manufacturer, model, color, size, storage, and camera megapixels using printf so that you get ASCII formatted data instead of the raw data that may be in some of those fields. Below that on line 22 is an array, is the declaration of an array of structs. We talked about this a couple of times, I think. But if you have more than one struct, you can put them in an array, just as you would make an array of ints or an array of characters. So phone my phone bracket 5 says there's create an array of phone structs up that will hold up to 5 phones numbered from 0 to 4. We're only going to use 2 in this example, but we've got the extras if we need. Here's the main function, and here we're going to see a couple of things. It's a little bit different. The F opens all look very similar for all of the IO methods that we've seen. However, this one's a little different in the sense that it's opening an output file. So, and it's opening it for write. Before we were opening that input file, unauthorized spread.txt, and we were opening it for read. You have to be very careful when opening a file for write, because if the file does not exist, it will be created. That's probably okay. If it does exist, it will be instantly overwritten. So if you had a phones.dat out there that was really very important to you and had hundreds of phones defined in it, this statement right here would pretty much wipe it out. So you have to choose that name very carefully. If for some reason the file should fail to open, we're going to print a message and leave. That's pretty unusual for a file to fail to open. Files fail to open for read for many, many reasons. You spelled the name wrong, you got the path wrong, and so forth. Files open for write usually open okay because they get created right on the spot. Here we begin. We already have 5 phones structs created. Here we're going to populate the first 2, the 0th and the 1st, by stir copying the strings in and by setting the floats and ints to numerical values. So these are actually instances of phone, right? So if you think of these manufacturer, model, size, and color as being attributes, then the actual phone's elements in the array are instances. It's almost as if you had the columns in a database, and these were the database columns: manufacturer, model, size, and color, and each phone in the array was a row in that database. There is pretty much a direct analogy between what we're doing here with creating structs and writing them out the disk and reading them back in with what databases do all the time on your behalf. Just to make sure that things are working correctly, we'll just, having populated those 2 structs, we'll just print them out using the print phone method defined above. That ensures us that they got properly populated. And we're going with a loop because it's an array. So we're going to loop through 2 phones, 0 and 1, and print them out. Here's the new stuff. This is an fwrite. So here I'm going to write those 2 structs out to another file. What file? Well, whatever I opened FP to. I opened FP up here to create phones.dat. So this fwrite here is going to put data into, it's going to open create phones.dat, which if it doesn't exist, it'll create it. If it does exist, it'll truncate it. And then we'll write those 2 phones out, those 2 phone structs out into this file. Now, the part of this that you may find odd is here, because the syntax looks pretty complicated. Ampersand my phone bracket I bracket. Let's analyze what that expression actually means. You probably know that when the ampersand appears, the and sign character, this one, that means to see, take the address of this thing. Don't give me the value, but rather give me the place in memory where that variable lives, which is, I need that in order to be able to change the variable. My phone bracket I simply selects either the 0 phone or the 1 phone or the 2 phone up to 4. So the loop is only going to go 2, so we're actually only going to get the address of the first phone and then the second phone. The size of my phone sub 0, size of is a built-in function in the compiler where the compiler will figure out for you how big a struct or any other type of variable is. And it's really convenient because your only alternative is to do this, which is to say, okay, let's see, it's how big is it? How big is a phone? It's 50 plus a float's probably 8, that's 58. Another 50, that's 108, another 50, that's 158, and another 50, that's 100, and you can see I'm getting lost. Plus, I'm not sure that a float is 8 bytes on this machine. I'm also not sure, this is a subtlety of C, that these items are really right next to one another in memory. There could be what's called padding in between a couple of these files. In order to get things lined up, most CPUs insist that numerical variables start on a word boundary, either an even numbered address or a 1 in every 4 addresses. That makes their life a lot easier. It makes the machine code run more efficiently. So the compiler might actually insert secretly some padding into the structure to move later elements of the struct, like that float camera megapixels, down a little bit in memory to make it line up with what the CPU expects. That's not something you want to try to figure out in your head. Right? That's compiler dependent, it's machine dependent, it's lots of stuff. We don't need to do that. We can use size of, and size of will look at that actual struct, phone struct, however it got represented, padding, no padding, avoids my bad arithmetic, and just comes back with a number, which is the actual size of the struct. So that's really handy, and that's pretty much required. Remember, fwrite, like fread, takes almost the same arguments. It takes, this is the data. With fread, this is where the data gets pulled into your program. With fwrite, this is where the data comes from, the data that's going to disk. This is how many bytes to write, because fwrite just writes bytes. It doesn't really know anything about the internal structure of your struct, except how big it is, which is what size of told it. We're going to write them one at a time. We could write more than one at a time. We're going to write them to wherever fp points. Remember, because of our fopen, it points to phones.dat. Then we're going to close fp, which is particularly important for 2 reasons in this example. One is that ensures that any data that was being held in memory for lazy writes actually gets flushed to disk by the program. And secondly, we're going to turn right back around and reopen fp to read the file. So we opened it, we wrote it, we closed it. We're going to open it again to read it, and close it. We're going to use the same file pointer to the same file, but we're doing different kinds of operations. So we need to close in between. So here's an open for phones.dat, and I check again, just in case it's not there. I mean, I just wrote it. I don't see why it wouldn't be there, but it can't hurt to check. And this time I'm opening for read before I was opening for write. And if that check fails, we quit with an error message, because there's really not much we can do except figure out what the problem is. And if it succeeded, we fread. It looks like I'm only going to read one phone. Well, that's fine. So fread into my phone 0, the first element of my phone array. How big is it? The size of a phone. One of them from fp, and then we'll print that out. And as you might guess, I forgot close, just for tidiness. And I might as well print both phones. So let's just make a loop here, starting with 0 for 2 phones. And let's put the print phone in here. So instead of just hard coding printing only the one phone, let's print both phones. And so instead of a hard coded 0, we want I. So this is actually going to loop and print both the iPhone and the LG or G3 or whatever the other phone was. Both of the two structs that we populated. And then we're going to F close. And just for tidiness, we're going to make the compiler stop whining. We're going to return 0. Main does return a value. If you say int main, which I think I did, you need to return a value. That value is probably going to get ignored by the operating system, but it's there if some script wants to look at it. Okay, let's see if that's going to compile for us. I'm going to go ahead and make this window a little bigger down here. This is a terminal window, a bash terminal window. And let's try compiling this. I'm going to use GCC. I'm compiling at the command line because in my ancient version of Visual Studio Code, that's pretty much the only thing that works. You know what? It's not really very hard. It's a little more typing the first time. After that, you just keep pressing the up arrow. And we're going to call the output file phone run me. Picking the output file name here is very important. If you put your .c file there again as the output file for the compiler, you're going to wipe out your .c file. We don't want to do that. So let's compile phone test.c and get hopefully phone run me. No warnings, no errors. The warnings are probably turned way down, and we probably did miss some warnings that we might want to take a look at if this were a production program. But this is probably good enough for the demo that we're going to do. Okay, let's run the program and see what output we get. Hopefully not a crash. Okay, we have to look back at the code to see what the output means. But we're already doing well because if you look, before are the lines that were printed just using printf. We hadn't fread or fwritten anything. We just populated the structs and we printed them out. Then they look pretty decent. After is what they look like after we fwrote them out to the file and fread them back in. And guess what? They look exactly the same, which is good because if they were different, we must have done something wrong. Fwrite just writes bytes. It doesn't change anything. If you fwrite something out, you ought to be able to fread it right back in, as long as you use the same struct definition in both cases. Let's take a quick side trip and look at what is actually in that phones.dat file that we created. So let's look at, I'm opening it in Visual Studio Code. And if you do this, this one's already open, but Visual Studio Code will complain this is not a text file. And then it'll say, do you want to open it anyway? It's not a text file. And I do want to open it anyway. So I'm going to open it. And sure enough, there's, actually, let me just see if I can, that's, I can probably reload it and get the right one. Let's see. We'll look at this one. It should have another record because the new phone.dat file will have two rows in it, but that's okay. Gold, where did that come from? Gold is the color of the iPhone, right? But what are all these little things here? Well, doubtless you can't see that in the resolution of YouTube in your monitor, but they say null, 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 null. They say 0. That makes sense because how big is the color field? 50 characters. But I only populated it with GOLD, 4 characters and a null. So when I look at it, I see the 4 characters and everything else is zeros because that's what I filled the struct with to begin. Large is the size of the phone. I think we had that here. Size is here, but in between was a float. This thing here, funny Unicode character followed by capital B, must actually be a floating point number. Why does it not look like a number? Because it's not, it's in binary. It's not an ASCII. And we read it back in. Remember, fread doesn't convert anything. So it just picked up however many bytes there are in a float and threw them up there. That's why it looks funny. Large is the size, followed by a bunch of nulls because it's 50 characters. iPhone 13 is the model, followed by a bunch of nulls. Apple, so forth and so on. And this is probably another float. So not a very useful way to look at binary files, because really the only way to look at binary files that makes any sense is to read them back into structs. But I did want you to see this, because if you're tempted to peek at the output file that your program wrote, and you may be, and it's entertaining, don't be fooled by the fact it doesn't look like what you expect. What counts is what you get when you fread it back in. So that's basically the round trip for fwrite, fread, which is basically project 8, I think. We're using an array of structs. I'm going to ask you to use an array of structs. And that's it. So if you follow this example and adapt it to the topic you've chosen, I think you'll find it's going to be helpful. That's all I've got, folks. Thanks a lot, and I will talk to you later.